Homework solution 2.7. Calculate the amount of current registered by each ammeter and the amount of power dissipated by each load. If someone were to multiply the value from the ammeters by 120 volts, would the resulting calculation agree with actual power dissipation? Why or why not? So what we're asked to find in this problem statement is, remember, ammeters just measure current magnitude. So we're asked to measure the magnitude of current 1, the magnitude of current 2, and the magnitude of current 3 here, since that's what an ammeter would tell us. It also asks us calculate the total power. So by power, we now mean P1, P2, and P3. In power systems, when the word power is used, that almost exclusively refers to real power. So that's what we're asked to do here. So we can determine the magnitude of current 1 here just by taking the magnitude of the voltage that's applied to the circuit and dividing it by the magnitude of the impedance. We saw that in the last problem. So we know that that's 120, but we don't know what total circuit impedance is yet. So Z is going to be equal to 240 in parallel with 1 over J 2 pi. Frequency of the system is 60 hertz. And then the capacitance is 10 e to the minus 6. So if we do that, we get 177.97 at an angle of negative 42.14 degrees ohms. I know this is written in polar form, but the reason I did that is because I can just, if I write it in polar form, I can extract the impedance magnitude directly. From polar form, you can't do that if it's in rectangular form. So I just get 120 over 177.97. So it's going to give me the magnitude of the current. Right? You may be asking, where did that come from? Remember, I is equal to V over Z, which looks like this, which is just equal to magnitude of V over magnitude of Z at phi sub V minus phi sub Z, the difference between the phase angles. So the magnitude of the current is just the magnitude of the voltage divided by the magnitude of the impedance. So I'm using that fact here. And that gives me a magnitude, a current magnitude of 0.674 amps. It's equal to the magnitude of I1. So I need to determine the power through this circuit, and I know it's tempting to use the current, but remember the ammeter is located here, so that's total current flowing through here, not necessarily the current flowing through the resistor. I do know, though, that because those two are in parallel, that there is 120 volts across that 240 ohm resistor. So I am going to use that the power is equal to V star over Z star, which is just the same as saying the magnitude of V squared over Z star. That's going to give me apparent power. I can just then extract the real power from that, and that's pretty easy to do for a resistor, because I can just say 120 squared. The impedance of that resistor is just 240. Since it's purely real, there is no complex conjugate associated with it, and that's just going to give me 60 watts. So S is just going to be equal to 60 volt amps, or 60 watts in this case. So that's equal to P1. In the case that there is no reactive power, the real power and the apparent power are the same. Technically, apparent power would be measured in volt amps, but that's okay. So for circuit 2, I've just got an incandescent lamp, so that's fairly easy. I've got the magnitude of I2 is just going to be the magnitude of the voltage divided by the magnitude of the impedance. I don't have to do any calculations, extra calculations there. That's going to be 120 over 240 is equal to half an amp. And I know that this is all that current is going through that resistor, so I can use P is equal to the magnitude of I squared R. That's going to be 0.5 squared times 240. It's also equal to 60 watts. I could have used IV. That would have been 0.5 times 120. It's also equal to 60 watts. So all the methods work. You just have to apply them correctly. Last, we need to determine I3 here in the series RL branch. And so what I am going to say there is that the total current through here is just going to be the V from that node to that node divided by circuit impedance. So magnitude of I3 is going to be equal to the magnitude of V over the magnitude of Z. So that's going to be equal to, well, I need to determine what Z is here, but that's going to be 120 over the magnitude of that resistor plus J 2 pi F, which was 60, times L, which was 0.25 henries, I believe, or was it 0.2? Yeah, 0.25 henries. So there we go. And we end up getting, finish off that magnitude statement. So the magnitude of Z there is going to be equal to the magnitude of 257.84 at an angle of 21.44 degrees. That's ohms, so magnitude of Z is just equal to 257.84. So can determine the magnitude of the I3 current. That's going to be 120 over 257.84. And that gives me a value of 0.465 amps is equal to I3. All right, to determine the power in the third branch, the real power is going to just be equal to the magnitude of I squared R. That's going to be 0.465 squared times 240 for the real portion of that circuit. That's going to be 51.894 watts. The last question was, if you took the value from the ammeters and just multiplied them by 120, would the resulting calculation agree with actual power dissipation? Why or why not? For the fluorescent lamp circuit, the current that we measured isn't the current through the resistor, it's the current through the total circuit. And we only need the portion of that current that goes through the resistor to determine power. So for the case of the fluorescent lamp, multiplying the value from the ammeter by the voltage from the voltmeter does not give circuit power because it's overestimating the current flow to the resistor. You can say that IR is not equal to I total. For the incandescent lamp, there's only one element. All of that current is flowing through that element, and all of that voltage is applied across the terminals of that element. So for this case, multiplying the voltage by the current does give you the resistive power dissipated by that incandescent lamp, since all of that is going through there and it's purely real. For P3, although all the current is going through the resistor, the voltage is split between the voltage divider of the inductor and the resistor right here. So part of the voltage gets dropped over this inductor, part of the voltage gets dropped over the resistor. Therefore, the resistor doesn't see the 120 volts AC across it. It sees a fraction of that, and so multiplying 120 by total series current there would not give you the power dissipated by the induction motor. You'd have to use the voltage across the resistor to do that calculation. That current times the voltage across this resistor. So in that case, no, multiplying 120 by current does not give you power dissipated in the induction motor.